Alright, so let us now see application 2, the second application of the class equation of a group. So this is the general Cauchy's theorem. You remember we proved Cauchy's theorem for abelian groups at the end of the section on homomorphisms. Here the group is not necessarily abelian. It may be non-abelian also, but it's a finite group, of course, whose order is divisible by some prime number p. Then, just like before, G must have an element of order p. So let us now see how this can be proved. The proof is by induction on the order of G. We apply induction on the order of G. The claim is vacuously true if the order of G is 1. Note that the claim is after all an implication. If P is a prime dividing the order of G, then G has an element of order P. So when order of G is 1, no prime divides the order. So the implication in this case has a hypothesis, that is P dividing 1, which is false. So that's why the implication is vacuously true, and this is the basis for our induction. Now we are going to make the induction hypothesis. Let G be a group such that, okay, I think we should mention that G is a finite group. Let G be a finite group such that, although these things are not mentioned here explicitly, but you understand that in the scope of this discussion, G is finite, such that the order of G is greater than 1. Suppose the claim is true for any finite group T such that the order of T is strictly less than the order of G. Now our aim is to, so this is our induction hypothesis, this supposition. Now our aim is to prove that G also has an element of order P. Okay. Now if there exists, and also one more thing that we have not actually mentioned here is that this condition is there in the background, that P is some prime dividing the order of G, even for this G. Okay, that we are not again writing, of course. So now we are going to consider some such condition involving P, but involving not the entire G, but a subgroup of G, a proper subgroup of G. Now if there exists a subgroup W of G such that W is different from G, that means W is a proper subgroup of G, and P divides the order of W, then we can apply the induction hypothesis on W, because its order, since it's a proper subgroup of G, the order would be less than the order of G. So on it, the induction hypothesis is applicable. But then W would have an element of order P, and hence G would have an element of order P. So in that case, we would be done. Then by the induction hypothesis, there is an element X in W such that the order of X is P, but then we have found an element X also in G such that its order is P. So in that case, we are done. So that means now we can consider the other possibility, namely in which no proper subgroup of G has its order divisible by P. G of course may have proper subgroups, but none of them is, it has an order that is divisible by P. So we now assume that P does not divide the order of H for any proper subgroup H of G. Any subgroup H not equal to G. Any subgroup of G that is understood, we are not writing it again. Now, we know that for any element A in G, the normalizer of A, that is NA, N of A, is a subgroup of G. Also, NA is a proper subgroup of G if and only if A is not a central element of G. If A is a central element of G, then NA is equal to G, and conversely, if NA is equal to G, then A is a central element, which means that if NA is not equal to G, that is equivalent to A not being a central element. Okay, now we are going to write the class equation of G. The class equation of G is, well, the actual class equation is not going to appear at once in the form that I am going to write here, that is, which involves the order of the center. But because in application we have already seen how that happens, so we are just directly going to write that itself. So this is your class equation, order of the center of G plus summation order of G divided by order of the normalizer of A, where A is not a central element. But of course we have to also write about this sum, that is how the sum is varying. Sum is varying means how many terms there are. We have to write about that. Where the sum has one term for each conjugate class that, well, how should I write it? That does not correspond to a central element. Or more positively, I can write like this, where this sum has one term for each conjugate class that corresponds to non-central elements. What that means is this. This is your, I'm going to draw a diagram here. So this is your group. Now the conjugate classes partition the group. We already know these things, and that's how we in fact get the class equation. So it's the fact that each central element creates a conjugate class of its own in which that is the only element, and non-central elements create conjugate classes which have more than one element. So the central elements create single conjugate classes like this. Single conjugate classes means singleton conjugate classes. So all of these things are conjugate classes, and each one has only one element, and all of them are central. The other conjugate classes which correspond to non-central elements, each one of them has at least two elements, maybe more than two elements, which is why when we write the class equation, we add that many ones as many central elements we have in the group. So that gives us this order of the center, and the other conjugate classes have their own sizes, which of course come like how they usually come in the original class equation, but they correspond to these other non-central conjugate classes. So what this part means is that we are taking one element A, and corresponding to it we have one term in this sum, and that element A is a non-central element, and this we are doing by taking one A from each conjugate class, exactly one A from each conjugate class. So the number of terms in this sum is equal to the number of non-central conjugate classes. That's what all these things mean. Okay. Now we are going to look at this ratio. If A does not belong to the center, you understand that this A is actually after all in G, but it's not in the center, it's a non-central element. Then NA is not equal to G, and so by our assumption, P does not divide the order of NA, because we assumed we are currently in this case where we have assumed that the proper subgroups have all of their orders not divisible by the prime P. So this is a proper subgroup, this normalizer, so its order also is not divisible by P. But P of course divides the order of G, so P must divide the order of G divided by the order of NA. Well, there are a few things to note here. The first thing is that this quotient actually is an integer that comes from Lagrange's theorem. We know that since NA divides the, NA is a subgroup of G, so its order divides the order of G. So you are going to get a positive integer here, and we are saying now that that integer is divisible by P. From these two conditions and the primality of P, it follows that we have this. But let's see exactly how that is true. Note that, well, I think it will be better if we name this something. No? Let K be this quotient. Also, let the order of G be equal to P, say J, for some J belonging to the set of natural numbers. In this text, the set of natural numbers does not contain 0. It means all the positive integers. Okay. Then what is it that we are getting? If we now write order of G in terms of this K and order of NA, then we are going to get K times order of NA is equal to, let's keep the class equation, okay, and continue from here, because we have to be able to see the class equation and then we can conclude. So this will be equal to Pj. So Pj is equal to K times order of Na. So that means P divides K times order of Na naturally, because it's a multiple of P. Thus, P divides K times order of NA. But P does not divide order of NA. Since P does not divide order of NA and P is a prime, we must have this. That's because we know that when a prime divides a product of two integers, then it has to divide at least one of them. So if it's given that it's already given that it does not divide one of them, then it has to divide the other. So that's why P has to divide K. And from there we are getting this. So this is the explanation behind that conclusion. Okay. Now you look at the class equation. What we have found here is that for each non-central element, this ratio is divisible by P, and precisely that type of ratios or that type of quotients are appearing in this sum because each one of them corresponds to a non-central element. So that means in this sum, each term is an integer that is divisible by P, and the left hand side is also divisible by P because that is our hypothesis. So P divides, in fact we can take one more step before we fully use the class equation. This. Hence, from the class equation, we get this. P divides the order of the center. P divides this, P divides that, so P also has to divide this. Now, since the center of G is a subgroup of G, so our assumption will have an effect here. What was our assumption? Namely that the order of no proper subgroup of G is divisible by P. Now here the center has been found to be a subgroup of G whose order is divisible by P. So that means it cannot be a proper subgroup. Since this is a subgroup of G, our assumption then forces us to conclude that the center is equal to G. But then G is abelian. So we have come back to the case where G is an abelian group, and for abelian groups we have already proved Cauchy's theorem. So from Cauchy's theorem for abelian groups, we get an element X in G such that the order of X is equal to P. So this completes the induction. and it also completes the proof. Okay, so we have handled two cases. In one case, G has a subgroup, a proper subgroup whose order is divisible by P. But then what we are trying to achieve, that in that case we get it immediately just from the induction hypothesis. But if that is not the case, if G has no proper subgroup whose order is divisible by P, then also we have achieved this result. So that just closes everything. And let me just also end the video here itself. After this application, we have a description of the relation of conjugacy in the class of symmetric groups. And using that thing, that description, some facts about symmetric groups come out. So this we are going to see in the next group theory update. And the next update, our next upload is of course this, what is today is Tuesday, no? So this coming Friday. On Friday, let's do calculus. So with that, I end things here for tonight. So see you on Friday with calculus. Until then, this is me, Lucifer from a mathematical group. Have a nice night.